Hello, everyone. Welcome to chapter 15.5. We're adding another integral into our double integrals, and we're creating triple integrals now. And there's really nothing different from these guys than double integrals. You evaluate them the exact same way. It's just that, setting them up might be a little harder. And so that's going to be the focus of this video then, is that we're just going to set up a triple integral. And the problem we're going to attack then is going to be 15.525, and you can follow it in your textbook. There's actually a picture in there, but we're going to do this the hard way. We're going to brute force set it up by only using the description of the problem, and we'll see how to do this in a little bit. So let's then give the problem. We have a region in the first octant. All right, bounded by the coordinate planes y plus z is equal to 2, and x is equal to 4 minus y squared. All right, so this is what we have. So what is the first octant? Well, if you draw the xyz axis, right, so this guy is x, that's y, this is z. The first octant essentially is then just everything above 0, right? So it's going to be like a cube, like here, like this cube then would lie in the first octant because x, y, and z are all bigger than 0. All right, so that's what the first octant is. It's just that, all right, we're given these conditions that x, y, and z, x bigger than 0, y is bigger than 0, and z is bigger than 0. Okay? So that's first octant bounded by the coordinate planes. So that's x. So that's those three guys. And then we got these two planes as well. So how do we set up our triple integral, right? Set up a triple integral. dv will get us the volume of this surface, which is what we're trying to find. So we're trying to find the volume of this shape right here. And again, your book has it. I'm not even going to draw it because I want to just be able to brute force it out from octant, brute force it out from just description. So, all right, so what is dv? dv is just dx, dy, dz, dx, dz, dy, dy, dx, dz, etc. Right? You guys get the idea. It's just any combination of dx's, dy's, and dz's. And so in double integrals, it was easier because we only had dx and dy, so there would only be two combinations, right? You'd either do dx dy or you would do dy dz. Here you actually have 6 combinations. So how in the world do I know which way would be the easiest to set these guys up? Well, I made an entire video in 15.2 talking about how we need to list out each equation by variable. So what do I mean again? Well, we need to take a look at, for all x, how many equations do I have where it's just x equals something, right? And so how do I do that? Well, okay, so how do I find out what x has to be equal? Like, how many equations do I have x is equal to something? So here we go. These guys up here, I kind of messed up. These should be less than or equal to, right? Or they're bounded by, right? They're bounded by these planes, so these are really like equal to 0, right? We're bounded by the z is equal to 0 is the xy plane, okay? Y is equal to 0 is the xz plane, and x is equal to 0 is the yz plane, right? And you can see that because z is equal to 0 would be this guy, right? That's a z is equal to 0, so it's the xy plane. All right, so hopefully that makes sense. But yeah, so now we just need to pick out all the equations that have x is equal to something. And what are they? Well, I have x is equal to 0, which is part of my first octant bound. So I have x is equal to 0, and then I have this equation, x is equal to 4 minus y squared. Okay? And then I need to list out all my y equations. And what do I have? Well, okay, I have y is equal to 0. I have y plus z is equal to 2, so that's also y is equal to 2 minus z. But then I got this guy right here, right? And what is this guy? Well, this is really y squared is equal to 4 minus x, and we need to break this guy down into a singular y and not like a y squared term. And so we get y then is equal to plus or minus, right, root 4 minus x. And so if we write that out as two separate equations, then, all right, we see that, okay, here we go. So y has 4 equations associated with it. How many equations does z have associated with it? Well, we got z equals 0, and then we got z is equal to 2 minus y, okay? And now, how do I set this integral up, right? Well, this triple integral. Well, what's the one variable that we don't want to integrate with respect to first? Okay, does anyone have any idea? Well, it's going to be y, right? Because y has four bounds, or has 4 variables associated with it. So if I set dy and then d something, right? I only have 2 bounds on the inside for y to be equal to something, but I have to capture all 4 of these variables, right? And so there's your problem there. Right, I have 2 spaces for bounds, I have 4 equations I need to include, so we're not going to integrate with respect to y first, okay? So integrating with respect to y is off the table first, so that's the only one we can't do. And then what's left then is dz or dx, right, because they both have 2 variables, and here it really doesn't matter. It actually just doesn't matter what you want to integrate with respect to first. So what I'm going to choose then to integrate with respect to first is, let's just do dz, why not? Right, so let's do dz first. So now, one of these guys, right, has to be z equals 0, and the other one has to be z equals 2 minus y. And which one goes on the bottom, which one goes on the top? Well, since we know we're in the first octant, right, that means x, y, and z have to take on positive numbers, right? And if you let's say y is equal to 0 here, then z is equal to 2, which means this guy is going to be above z equals 0, right? It's going to be bigger than z equals 0. So that means z equals 0 is likely going to be the lower bound, and then 2 minus y is going to be the upper bound, right? And if you look at the picture, and you do the same thing, in the picture you would draw a line parallel to the z-axis through our region from negative to positive and see what it hits first. And I guarantee you're going to hit z equals 0 before you hit 2 minus y, okay? All right, so that's the dz integral. That's fine. So now let's look, what should we integrate next? Well, dx only has 2 equations as well, right? And so that seems like a good candidate to integrate second. And I agree completely, because then dx is just as simple from 0 to 4 minus y squared, okay? So, cool, that's going to be what x is going to be. And now what's y, right? What is y going to be? So, dy is going to be our last guy, and the outer integral, right, has to be constants. These guys have to be constants, right? And essentially it is what is the biggest and what is the smallest value that y can take on in this region. And so, well, this guy right here, right, this guy is going to be a negative value, so we should have just dropped him anyways. Makes sense, right? Because it's a negative square root of 4 minus x, so this is always going to be a negative value, but we're in the first octant, right, where these guys are all positive. So yeah, so we got to drop that guy. So y really only had 3 equations, but still, we weren't going to use it anyways. Okay, so now dy is our last variable, and we need to find the smallest value y is going to be and the biggest value y is going to be. Well, what's the smallest value y can be? We're in the first octant, right? So we have to be bigger than or equal to 0. So y has to be bigger than or equal to 0. That's going to be the lower bound. And what's the largest value y can be? Well, if we look at these guys right here, right, it looks like y can take on the value of 2 when z is 0, right? So here, if z is 0, then y is 2. And here, if x is 0, it looks like y is 2 as well. So then it looks like, oh, y, the largest value y can take on, is going to be 2. All right, and so this is going to be my integral, and now I just integrate it, and what do I get? Okay, so that's equal to the triple integral. If I integrate with respect to dz first, now I get 2 minus y, right? And then these other bounds stay the same. And then finally, now I have dx, so now I go from 0 to 2. I got 4 minus y squared times 2 minus y. And then dy. And then so now foiling it out, 0 to 2, 8 minus 4y minus 2y squared plus y cubed. All right. And then dy, and now we integrate this with respect to y, so we get, no more integral sign. 8y minus 2y squared minus 2/3 y cubed plus y to the 4th over 4 from 2 to 0. And then that's, if you plug that in, what is that? 16 minus 8. That's 8, 16 minus 16 thirds. And then 16 plus 4. And so you get 12 minus 16 thirds, which is equal to 20 over 3. And so that should be the volume of this region defined by the problem in 15.5.25. So this part down here is just the integration. It's just the algebra. And if you guys want to see what the sketch of the region looks like, again, it's number 25 in your book, but we might as well just show it in the picture here. That's what it is right there. And yeah, I think it's pretty believable that region is going to have an area or a volume, right? We're dealing 3 dimensions, so it's volume of 20 over 3. And I'm just going to double check real quickly to make sure I have the right answer, but I likely do. This is a pretty typical integration problem for triple integrals. And yeah, I do. Okay, cool. So, great. That's the problem, and hopefully this makes sense. Setting up triple integrals makes sense. The biggest thing when we set up triple integrals is we need to know how many equations of each guy we have, right? And so, yeah, if one of them has more than 2, then obviously you're not going to go with that one first. So that's it for 15.5. I don't think I'm going to do any more videos for 55 unless I can find like a really tricky example. But I think tricky examples I'm going to leave for recitation in review sessions. So, all right, next chapter is 15.6, I believe, which is, I think it's like the chapter on mass and like moments of inertia and stuff like that. It's by far my least favorite chapter. By far my least favorite chapter in this entire course. I'm going to probably just do a mass problem. Moments of inertia get really calculation heavy, and you don't really see these guys on exams anyways. And I'm pretty sure that they made it optional for fall 2018. So I'll probably try to talk my professor out of it, but we'll see. Okay. So, yeah, next chapter 15.6, and then we're moving on to more triple integrals after that. So hopefully you enjoy this, because that's all it looks like for the next few sections.